Today, we're going to learn how the unordered set works. Hello, I'm James Helfrich. The standard template library has a container called the unordered set, which is actually a hash data structure. What is a hash data structure? Well, we have some containers which store things in the order the user placed them, like the vector or the array or the deck or the queue or the stack. There are some that sort them according to the less than operator, like the set or the map or the priority queue. The hash is different. Everything is stored according to a hash function. We're going to learn how the hash function and how the unordered set data structure works today.
The unordered set has a large number of constructors, including the default constructor, the copy constructor, the move constructor, which work just the way you expect. It also has the initializer list constructor and the range constructor, which will take a bunch of elements and drop them into the unordered set according to the hash function. We can specify the number of buckets. But the interesting thing about the unordered set is the template. We specify the data type, the hash function, and the equals predicate. In order to use the unordered set, we first have to pound include the unordered set library. Now the full name of the unordered set is std::, unordered set, and then you must specify the t, or the template parameter. And this will, of course, call the default constructor. I'm going to call this US for an unordered set. Now when I run this, it's going to tell me that my size is 0, and there's my hash function, my equal to predicate, and my allocator. The raw view doesn't really provide me a whole lot of data. Now I can also specify the initializer list, so I'll drop a whole bunch of values into my unordered set, 2, 4, 6, and 8. And when I run those, I expect my size to be 4. Now, Visual Studio and also Xcode give us a special view of the unordered set, which places them in order, although in memory they won't actually be in order, so that is a bit misleading. Now, if I put duplicates in there, then the duplicates will be ignored, so the unordered set behaves exactly like the ordered set. In other words, it removes duplicates. The size is still 4. All right, now the raw view, when I bust into here, it doesn't really show me the underlying data structure. It shows me it's a hash, but that's pretty much it. And so it's kind of not very useful. Now, one other thing I could do is the range constructor. So here I'm going to create a vector that has a bunch of elements. And then rather than specifying the initializer list, I'll specify the range of the vector, v.begin and v.end. And this will iterate through all elements in the vector and drop them into my unordered set in the order that I expect. There we go. Now the 4 elements are in there. Now, like I mentioned before, the Visual Studio and Xcode don't do a very good job of showing you the underlying data structure. So in order to illustrate how it works, I'm going to include my own homebrewed version of the hash of the unordered set, and I call it hash.h. And this is going to be exactly the same as the standard template libraries, although I'm going to use the custom namespace. And in here, we're going to get a really good idea of how this works. So my unordered set is going to have a buckets, which is going to be a vector, and that's going to be of capacity 4 and a size 4. And the first element is going to be a list. So on data 1 will be a list. This list is going to have 2 elements, and the first element is going to have data 4, the next will have data 8. In other words, the unordered set is going to be a vector of lists, where each vector index is determined by the hash function. Now by default, we use the regular built-in hash function for integers, which returns 1 for 1 and 2 for 2 and 3 for 3 and so on. But I can, it turns out, create my own hash function. So the hash function is class hash, or whatever name you want, and it has to have one public method, which is the functor, which is the operator parentheses. And I'm going to take a constant, well, t, my t is an int by reference. This must be a constant method, and I'm going to return 1, so I'm always going to put things in the 1 bucket. So now I still have 4 elements, but in the 1 bucket, we'll see this list has all 4 elements. Has elements 2, 4, 6, and 8. So this is a very inefficient hash function. We really want our values be distributed normally, evenly across all the elements in the vector, all the buckets in the vector. But I'm going to put it all in 1 just to demonstrate how this works. Now when I put a whole bunch of different elements in here, once again, these are all going to go into slot 1, all 5 elements, and p head. So there's 5 elements, but in bucket 1 is where all 5 elements are, and 38, 21, 99, so they all got dropped in the order in which I placed them. Okay, there are two different ways to assign elements to an unordered set, the assignment operator and the swap method. To demonstrate how this works, I'll have one unordered set called US source, and then I'll have another one called US destination. And then now I'm going to copy the source into the destination, use the assignment operator. And now I expect to have both the source and the destination have 5 elements in it. Not only will they have the same number of elements, but the buckets will be in exactly the same order. Oops, I forgot to change this to US source. Oops, SRC. And then, of course, that's going to have 5 elements in it. And the same is going to be true with destination. It's going to have 5 elements in it. There we go. And when I look at bucket 1 in source, because remember I'm using the hash 1 that I just created, which puts everything in the one bucket, is going to have all the elements in it, just like before. And destination will have exactly the same structure, because it's just going to copy the buckets one by one. Okay, now I'm going to have the source use a custom hash function, but the destination will not. And now I'm going to get this crazy compile error, because the assignment operator requires the left-hand side and the right-hand side to be the same data type. And if the template parameters are different, it's not compatible. But now that I both have the same template parameters, now I'll be able to do the assignment the way I expect. Notice that in bucket 1, I only have 1 element, where before I had 4, and that's because the default hash function distributes the elements that we put in more evenly, whereas my custom hash function always put things in bucket 1. Now I can also call the move assignment with std::move, and this will move everything from source into destination, which means source will be empty and destination will have all 5 elements. And sure enough, source and destination. And the last thing I could do is swap, and swap will replace the contents of source with destination and vice versa. And when I'm done here, then source will have 0 and destination will have 5. And it works. There are 2 types of iterators with the unordered set. There's a regular iterator, which goes through every element in the collection, and also there's a local iterator, which iterates through a single bucket, and to get it, we must specify the bucket number. Now, the full name of the iterator is custom : unordered set *int : iterator, and I call it it. Now, of course, if I was using the standard template library version, do the spd : unordered set. And this will give me a pointer to the first element in the collection. Now, if I expand it under it list, because it list is going to be a single bucket, then I have data, which is 21, and that is the first element in the first bucket. Now, we're going to say, wow, that is a really long declaration name, but fortunately in C++ 20, then we can use auto, and there we go, I can use a much nicer name, and I get number 21. Now, the full name of the local iterator is unordered set int : local iterator, and we'll call it local. Now, to get it, I say unordered set.begin, and then I have to specify the index of the bucket I care about, and I'll say bucket 0. Let's see what's in bucket 0. So I go local iterator, and what am I going to find in here? Well, apparently 21 is the beginning of bucket 0, and when I say bucket 1, what's the beginning of bucket 1? It looks like the value 26 is the beginning of bucket 1. Now, how do we access elements from the unordered set? The same way we do with the set, with the find method, both the read-only and the read-write version. Now, find will return an iterator, so I have to specify the data type, unordered set int : iterator. And now I'm going to find, let's see here, what should I look for? Yeah, I'll find 38. Now, 38 is in the set, so I expect an iterator pointing to 38, which will be somewhere in the unordered set. So I look at it list, P, and sure enough, it is 38. Now, what happens if I try to find something that, oh, and I can also say auto it, of course, that's much more convenient. When I run that, then list, there we go, and it's the same thing, 38. Now, I can also look for something I know doesn't exist. Like, let's say 21. Oh, 21 does exist. So I expect it to point to 21, and sure enough, it does. And what happens if I point to something I know does not exist? Let's say 100 maybe? How about 100? Then when I run it, I expect to find the n iterator, and the n iterator is when the pointer points to null, and sure enough, itList is the null pointer. We can also ask the unordered set what bucket a given element would be in. So the bucket function takes one parameter, which is the t, which is the element we want to query. In this case, I'm going to see what bucket 38 would be in, and I run it through the hash function, and it looks like it's going to be in bucket 3. And then let's do the same thing for 21. It looks like that's going to be in bucket 0. Now, if I specified my non-default hash function, then it would always return 1. I expect 1 to always be the answer. And sure enough, 1 is for 21, and 1 will also be for 38. And that's because of my silly hash function. There are several ways to insert elements into a hash. One of them is the insert with a copy and move. Then there's the insert with a hint, as in this is what bucket those should go in. Then, of course, we can insert a number of elements with initializer lists and the range insert. But the interesting thing is rehash. Rehash will change the number of buckets, causing all the elements to be reinserted into the hash table. And reserve will figure out how many buckets are needed based on the number of elements specified in the size, as well as the load factor also specified by the user. Okay, so first I'm going to insert the number 38. Now I'm going to take the return result and put it in auto return result. And I'll do that for a reason you'll see in a second here. 35. Now 35 is not currently in the hash, so I expect that so notice I'm going to return 35 and true, which means I was successfully able to insert an element. But if I say 21, 21 is already in the hash, and it'll return false, which means I was not able to insert a new element because the element already exists. And that's why my unordered set is the same size it was before. Now to see how rehash works, I'm going to have to take a look inside the hash function. So I'm going to have to use my custom version here. And I'm going to say rehash 10. Now before I had 8 elements, and now when I say rehash 10, I should have 10 elements in my underlying vector. And so there are 5 elements in the hash, but the vector itself has 10. And if I say rehash 20, then once again the unordered set has 5 elements, but there are 20 slots, or 20 buckets. There are 2 types of remove methods: erase, which will erase a single element or a collection of elements, and then clear, which of course will remove all elements from the unordered set. So I'll start with the standard template library's unordered set, and I'm going to say what happens if I us dot remove or clear. There, I'm going to erase 38. Now this is going to tell me how many elements were actually removed. And so I expect 1 because there's exactly 1 instance of 38. So the return result is 1, and size went from 5 to 4. Now, what happens if I try to remove something that does not exist, like 101? Then before, I had 5 elements, and when I step over, now I've removed 0, so I still have 5 elements. Note if I had an unordered multi-set, then I can remove more than 1 instance. And of course, I can always clear. When I run this, then my unordered set will become empty. And sure enough, I went from 5 to 0. There are many status methods provided with the unordered set. The usual size, the bucket count, how many buckets there are, the size of a given bucket with bucket size, the load factor, which means how dense we have elements to buckets until we have to reallocate new buckets. We can set or query the max load factor, and we can also get the hash function, the equal function, and even the allocator if we choose. Okay, so there are several status methods. The first one is size, just like every other container, and it's going to turn in the number of elements there are in the container. And this is going to be of type size t. And a size t is an unsigned integer. We also can get the bucket count, which is how many buckets there are in the unordered set. And we can get the bucket size, and that takes a bucket as a parameter. And this is going to tell us how many elements there are in a single bucket. Now all those are of size t. We can also get the load factor, and this is the ratio of the number of elements to the number of buckets. For an example, if there is 1 bucket for every element, the load factor would be 1, but if there are 2 buckets for every element, then the load factor would be 0.5. it's desirable to have a load factor of less than 1. In fact, I think research says the best load factors are about 0.75 or 0.6 or something like that. So right now we're going to ask the size of bucket 1. Now, we also can specify and query the max load factor. Now, by default, the max load factor is 1, which means 1 element for every bucket, which means if we try to add a new element when it's more than the number of buckets, then it's going to rehash. We can specify the max load factor to be anything we want. Like I said, 0.6 or 0.7 is probably optimal. And all these are of type float. So let's see what our current load factor is going to be. We're going to have 8 buckets by default, and there are 5 elements. So that means my load factor is going to be 0.625, and I think my max load factor is going to be 1 because that's the default. And when I run this, let's see what I get. Okay, so first of all, the size is going to be 5 because there's 5 elements. That's correct. The bucket count is 8 because that's the default. The buckets, there are 0 buckets. There are 0 elements in bucket 1 at this point in time. The load factor is 0.625, just like we computed, and the max load factor is 1 because that's the default. Now I'm going to run it again, and we're going to query the number of elements in bucket 0. We expect the size and the bucket count to be the same, but sure enough, there are 2 elements in bucket 0. Now I'm going to do the same thing again, except now I'm going to say unsortedset.clear, which means my load factor should be set to 0. My max load factor is unchanged, and the number of elements in a given bucket is 0. The total number of elements is 0, just like we expect. As you can imagine, there is a lot more to the unordered set and hashes in general than we covered in this short video. If you'd like to learn more about it, including how to implement your own hash, please take a look at the C++ data structures textbook. The link is provided in the description below.